Hi, I'm Gavin, and my co-presenters Franklin and Teresa will be joining later on in this presentation. But essentially, the title of our project for Math 222 is Modeling the Employment States of the Total Civilian Non-Institutional Population over the age of 16 in the United States using Markov chains. And the key guiding question that we always kept in mind when doing our analysis was, how do we exactly estimate the long-run unemployed, employed, and not in labor force proportions of the total civilian non-institutional population over the age of 16? And some intuition for the background regarding our project. The proportion of the population that transitions between three employment states is defined by month-to-month labor flows. For example, if 1,000 employed workers become unemployed between January and February, if we know the total number of employed workers in the first month, we can calculate the proportion of workers of employment state A that transition from state A to state B between months. And we can effectively treat these month-to-month transition proportions as a probability. For example, if 40% of employed workers become unemployed in the next month, we can treat this like a probability. There is a 40% chance that an employed worker becomes unemployed in the next month. But first off, why exactly do calculating these long-run unemployment steady states matter? Well, determining the long-run unemployment steady states enable economists to make predictions on the future direction of the economy, because ultimately, unemployment, employment, and these different labor states underpin the workings of the broader macroeconomy. And essentially, these long-run employment estimates provide a baseline for central banks to conduct monetary policy, which is crucial in our day-to-day lives in America.
So for our data, we used the labor flow statistics provided by the BLS from December of 1999 to February of 2024. The data was collected via personal visits, mail, telephone, email, and video calls from the ORS. Every month, the BLS announces the labor flow data of the previous month. The data is open source, and which we downloaded as a CSV file to be processed for our project. The data source provides the necessary data to answer our question, which is the number of people transitioning between the three labor states, employed, unemployed, and non in the labor force, as well as the total number of employed, unemployed, and not in the labor force. And this, of course, allows us to calculate the proportion of the population over the age of 16 transitioning between these employment states. So for some intuition behind the Markov chain, our question has the three possible states as we identified. And so, of course, Markov chains are the optimal method for answering these state contingent questions. An important assumption is that the employment state of the next month is only dependent on the employment state of the month prior. So we calculated the transition probabilities of the three states as shown below in the slide. And because we used month-to-month data, a step in the Markov chain represents the calculated employment state proportions of the next month. And lastly, the eigenvalue of the 3x3 transition matrix we generate when populated with the 9 transition probabilities associated with the eigenvalue of 1 represents the steady state proportion of the over 16 US population in each of these three labor states, which is equivalent to the long-term employment states of the US population. So on why we created three different transition matrices. So month-to-month labor flow data can vary due to the cyclical nature of the economy. For example, the proportion of unemployed workers becoming employed in the next month is probably greater during times of economic expansion when compared to recessionary periods. So we created three different transition matrices. The first is the long run, using the average month-to-month flow proportion data from December 1999 to February 2024. And the reasoning behind this is to really just smoothen out the business cycle fluctuations, provide a more accurate matrix model. The second was the recessionary period, which averaged the month-to-month labor flow data between December 2007 to 2009. And this is, of course, during the 2008-2009 financial crisis. And lastly, the expansionary period, which is the data between May of 2020 and February 2024, which utilizes the labor flow proportion data during the the COVID expansion period. And here's a little visual to show those periods. So, of course, this is the long run, as well as the red, which is the 2008-2009 financial crisis, and the green, the COVID expansionary period.
For our project, we used MATLAB because MATLAB handles linear algebra the best. The first thing we did was we loaded 16 matrices obtained from the US Bureau of Labor Statistics into our .mat file, so that way we can use for a MATLAB script. And each of these matrices represent a different thing, such as total employment, employment to employment, and so forth. And each of these matrices were 25 rows and 12 columns. The rows represent the years, such as from 2000 to 2024, and the columns represent the months. And here's an example of a matrix that was loaded into the MATLAB script. And as you can see, from row 25, basically representing 2024, to columns 3 to 12, they were filled with 0 because there's no data from March 2024 to December 2024. And this is also so that way it doesn't mess with calculating our averages. And so then we calculate the proportions for the following matrices: employed to employed, employed to unemployed, and so forth. And so we do this by using a calculate proportions function that takes into account a total matrix, the two matrix, such as employed to employed, and the value for December 1999. And so now the column names are January to February, February to March, all the way to December to January. And so this is where we use the first for loop. which calculates from January to February column all the way to November to December. And so let's actually take into account an example, employed to employed proportions matrix. And so if we take the first value, which is 2000 January to February, it basically divides the employed to employed value for February 2000 by the total employment value for January 2000, and does this all the way until the November to December column. And then the second for loop handles that special case where we're taking into account December 1999. The initial calculation involves dividing the two matrix value for January 2000 by December 1999 value, and then continues the same process as the first for loop. And so here's an example of the proportion matrix that was created by the create proportions function. As you can see, the rows are still 2000, 2024, but the columns now represent something different. As instead of January, February to March, it's now January to February, February to March, all the way to December to January. And so we also calculate the transition probabilities based on the average proportions. And so to do this, we created a calculating averages function for each of these three matrices of long run smooth, deep recession, and strong recovery. We basically sum up all the matrix and the values of what we want, as you can see in the deep and strong recovery matrices, and then we divide by the number of values that we're using. And then we have the transition probabilities I can see on the right-hand side. And so now it comes down to calculating the Markov chain and seeing what the final state vector is. And before we actually calculate the Markov, we first have to check if it's suitable for Markov chains. And so in order to do that, we have to make sure is the sum of the rows equal to 1. If not, then it prints out an error and it stops the program entirely. And also make sure that the matrix is a square, as you can see by this if statement. And then we have the Markov chain function. This function takes into account the matrix, the number of steps, the initial state vector, from employment, unemployment to not in the labor force, and then it calculates the initial state multiplied by the matrix to the power of number of steps. And then it spits out the final state vector.
So taking a look at our final results, we used 300 steps, a reminder that one step is equivalent to 1 month, as well as the initial state we used based on the most current up-to-date data provided by the BLS. And these are the final results generated by our model, showing the long-run steady states for each of the matrices we use for the long-run, deep recession, and strong recovery. Here are some visuals, firstly with a heat map coloring of the transition matrices, showing the probabilities of that saying going from employed to employed or from unemployed to employed, vice versa. We also looked at the flow states. And again, as an economist would expect, the majority of the transition happened within the same state, let's say from employed to employed or from unemployed to unemployed, but it also shows the relative probabilities of transitioning between the three states. And then lastly, we generated the time series graph of the convergence of the three labor states to the long-run steady state, as you can see. And it's the same numeric value as we presented earlier in our slides.
So how exactly do we interpret our steady state values? Well, when we interpret the long-run steady state values, which is when the eigenvector of our transition matrices is 1, it can either be interpreted two ways. Either first, the probability that a single non-incarcerated individual over the age of 16 in the United States will be in one of the three states in the long run. Because if we view this set of states as applying to a singular individual, these are essentially the probabilities that they will be in either one of these states in the long run. Or if we take a whole of a population approach, we can see that the proportions of the US population that is not incarcerated in over 16 years of age in each of the three employment states can also be interpreted from the long-run steady state values. And it is important to note that these are not traditionally defined unemployment, employment, and not in labor force rates, because the denominator is the sum of the unemployed, employed, and not in labor force populations. And hence, if you remember or recall from the slide previously, our calculated long-run unemployment proportion is 3.57% when using our matrix, which was the long-run smooth transition matrix. And ultimately, using the Congressional Budget Office's U-star, which is natural rate of unemployment, as a benchmark for the unemployment metrics calculated from our long-run smooth transition matrix, we find that U-star, as calculated by the Federal Reserve, is around 4.4%, and our calculated long-run unemployment proportion is 3.57% when using our long-run smooth transition matrix. And note that these two numbers can't be directly compared due to the reasons listed above. However, these numbers ultimately make sense. And the reason why our number is intuitively lower than the Fed's U-star can be explained by the fact that our proportion is calculated with an inherently larger denominator, because U-star's denominator is total labor force. Our denominator is total labor force plus not in labor force populations. And there are a few caveats when interpreting our results. The first thing is the assumption inherent to the Markov model. That is, the current state is only dependent on the previous state. And this is a bit simplifying and reductive when dealing with time series economic data. And additionally, unemployment is dependent on dynamic, ever-changing structural features of the United States economy that this model cannot anticipate in the long run. For example, future advances in AI taking all of our jobs. And this is also a reason why the Fed has stopped calculating the natural rate of unemployment, because it's really difficult and it's constantly shifting due to these unforeseen structural reasons. And we can apply our transition matrix to a hypothetical scenario. For example, during the COVID peak, which was between March 2020 and April 2020, the employment state proportions were as follows. 8.8% of the civilian, non-institutional, population was unemployed. 51.2% were employed and not in labor force, which was 40% of that population subsection. And using the above values as the starting states of a Markov chain with our long-run smooth transition probabilities, 62 steps would effectively return us to our steady state labor proportions, which is around 5 years. So by our calculated long-run smooth transition matrices, it would take 5 years for the US labor force proportions to recover from its pandemic peak, which is just interesting food for thought. So thank you so much for listening to our presentation, and we hope you enjoyed it.